let's go over some quick triangle properties. We're going to go over regular triangles, that it applies to all triangles, and then we're going to go over some right triangles as well. The problems are your homework, so that'll be what you do for the rest of the It's Learning. So looking at the first one, problem 1, finding missing angles. Inside of a triangle adds to 180 with its angles. So let's just start with the triangle that's on the right, that's got the 36, the 84, and then that missing piece. That missing piece is going to help us in a second. So if a triangle has to add to 180, we're going to do adding 84 and 36 together. 84 plus 36 is 120. If I did 180 minus 120, we are left with 60 degrees. So our 60 degrees is going to be this little angle up here. That's going to help us find our next missing angle. I'll let you guys solve the rest of it for part of the homework. Let's pop on over to similar triangles. There's 2, 3, and 4. Those are all similar triangles, just in different ways. Figuring out, do we remember our 3 properties? So does it have angle-angle similarity? Does it have side-angle-side similarity? Or does it have side-side-side similarity? Angle-angle means we have 2 angles inside of there that are are congruent. So like in this first picture, you have one angle that's marked. Those are the ones on the corners. And then we actually have vertical angles in the center. So I would say, based on the picture, since we don't know all the sides, I would actually veto side, 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 or side, angle, side. And then the angle, we have the pink angles in my picture, and then my vertical angles are congruent. So for B, they have angle similarity. So there's a freebie for you. In 3, it looks like we've got all the sides, so I wouldn't play around with anything with angles. I would check and see if the reason is side, side, side similarity. You'd have to check the ratio. If the ratio or scale factor is the same throughout, we can say yes, these triangles are similar. If even one of them's off, then we have to say no. So I'll let you play around with those. That's just thinking about it. Is it side, side, side? Yes or no? If yes, what's my scale factor for 3? In 4, these problems are the ones where we can see the 2 triangles with angle similarity because we have parallel lines. So in 4, I'm saying those are similar, okay? Take your time. Couple things to remind you. If you have an entire side length, like in the first problem where A is missing, you need to remember that we are putting A over the 20. They should be similar. And then the 4 over the entire length of the triangle. 4 plus 12 would be 16. So there's our setup for 4A. I'll let you guys try out E. That one's a little bit nicer. Feel free to use your notes. I'm not saying we can't use our notes with these. Backside. All about right triangles. We're going to find a missing side based on knowing 2 sides of a right triangle. So what if we need to do that? Do we use trig? Do we use Pythagorean theorem? Do we use inverse trig? If we have one missing side and we know 2 sides, Pythagorean theorem's the way to go. So if this is the case, use your a squared plus b squared equals c squared, where a and b are your legs and c is your hypotenuse. I'll let you do those problems. In the next case, if we have a missing side and we know an angle and a side, that's when we use our trig ratios. That's when we use our SOHCAHTOA. And if you haven't gotten started on your cheat sheet, that's going to be one of the first things on there. Reminder about SOHCAHTOA, you choose your angle. That is controlling what's the opposite side, what's the adjacent, and then your hypotenuse is always across your right angle. So just be careful, choose the angle, circle it, make sure you feel okay. You can draw all over these pictures. You should have the paper in front of you. With this one, we got missing angles and we know two sides. That's when we get to use our inverse sine, inverse tangent, inverse cosine. Those are going to pop out the angle. So inverse sine, inverse cosine. Fractions stay the same. They're just going inside the function. And then we got our inverse tangent, opposite over adjacent, popping out our angle. So again, the angle is controlling how to label things. So 11 is your hypotenuse for the first one, 8's your adjacent. Figure out which ratio we would use for our first picture. I'll let you solve for x for both. And finally, haven't seen these in a minute, special right triangles. These are helpful because you have to do less work. I like that. If you have a 45, 45, 90 triangle or an isosceles right triangle, your base angles are the same, so two of the legs are the same. Your legs match, and your hypotenuse is just simply your leg times square root of 2. Done. You could find that with Pythagorean theorem if you wanted. This one is only for a 45, 45, 90 triangle. So just be careful. Our other triangle has more rules. If you have a 30, 60, 90 triangle, your short leg, and in this case 14 is your short leg. It is across from your 30 degrees, so it should be the smallest side. Your short leg controls everything. My hypotenuse is my short leg. I'm just going to do SL times 2. And then my long leg is my short leg times square root 3. In this picture, X, is it your hypotenuse or your long leg? I would use your right angle to help you. You got your hypotenuse. And then Y is going to be our long leg. It's across from the 60. Overall, special right triangles are unique and they're interesting and they're just some shortcuts. So they're really nice to use, but a lot of times you can just use our regular stuff. We got trig to help us, we got Pythagorean theorem to help us. We can even use we can use similar triangles possibly. Okay, I'll be back in class hopefully Thursday. If you have questions, just email, let me know.